Hey guys, welcome back to Engineering Hack, where I try to solve engineering problems in a way that's hopefully easy to understand. We are continuing the 2021 exam on thermodynamics. This is question 3, part 1, because question 3 also has a part 2, which is actually a completely independent question. So we call it question 4, but the original title is question 3, part 1. And it reads like so. An insulated open feed water heater is used to produce a stream of saturated liquid water at a pressure of 5 bar that exits the open feed water heater at port 3. Compressed liquid water at a pressure of 5 bar and a temperature of 100 Celsius enters the open feed water heater at port 2. The mass flow rate of this condensed liquid is 2.5 kilograms per second. This stream of water is heated by a stream of superheated steam at a pressure of 5 bar as well, and at a temperature of 260 degrees Celsius, which enters the open feed water heater at port 1. So we have a lovely drawing of this here. We know that this port 1 has the 260 Celsius and pressure of 5 bar. Let's call that pressure 3 and temperature 3. We also know that we have water. This is superheated. We also have water, compressed liquid water, coming in at 5 bar and 100 Celsius on port 2. So this is T2, 100 Celsius, and P2 is also 5 bar. And this is compressed. It didn't need to tell us that. We could find that for ourselves, but extra information. And then these two guys combine inside the open feed water heater, and then they exit at 5 bar as a saturated liquid. So over here we have, this is not T3, this is T1, pressure 1. This is T3, pressure 3. We don't know T3. We know this is 5 bar, and we also know this is saturated liquid, as is said down here. Cool. So we are to write the appropriate energy balance for this process and determine the mass flow rate of superheated steam entering on port 1. So we want to know what is this guy here. It's right here in this corner. M1, what is M1? And write the appropriate entropy balance for this process and determine the rate of entropy generation. So it wants us to find Sgen, entropy generated. Brilliant. Okay, to be able to solve this, we're going to be using our property tables for steam, for water. And what do we have here? Let's draw this system closely. Actually, let me just see if there's any tips on this problem. Insulated, yeah, okay, so there's insulated there. Also, we know there's no Q going in or out. Yeah, either way, no Q, compress. Okay, cool. All right, so let's start our problem analysis by drawing what we have there. So let me simplify as much as I can. Cool. We have that open feed water heater. That's going to be our control volume. Okay, so I'm going to look at what's happening inside this control volume. And in terms of energy, we have energy coming from the steam. So that will be looking at energy rate. That's going to be M1, entropy 1 times mass flow rate 1. It's entropy because it's a moving fluid, right? Same thing here, mass flow rate 2. And then we have leaving this control volume, we have entropy 3, and then mass flow rate 3. So if I do a little energy balance on this, because energy cannot be created or destroyed, then whatever is going in has to be minus whatever is going out has to be equals to 0. So that means that H1 M1, and this is right, by the way, plus what else is going in? H2 is going in, minus what's going out, that's H3 M3. This has to be equal to 0. Brilliant. What else do we know? If we look at the continuity equation, so if we just focus on the masses, right? So long as the mass is not accumulating inside this open feed water heater, that is, we don't have more water over time, or the other way around, right? So long as we're not losing water. Let's say that the volume starts here, and then as time elapses, our volume goes down here. Then, as long as we don't have that situation, then we have a constant inflow of mass coming in and mass going out. If that's true, then we can apply our continuity equation, which tells us that obviously the mass flow rate in 3 has to be equal to the mass flow rate in 1 plus mass flow rate in 2, right? And we know that M2 is 2.5, so we can rewrite this as mass flow rate 1 plus 2.5, everything in kilograms per second. Brilliant. So we're looking for M1. Okay, so M1 equals, is it M1 we're looking for? Yeah, M1. We want to find M1. So in order to find M1, I can rewrite this equation here, because then M1 is simply M3 minus 2.5, right? So as long as I can find M3, I can find M1, which is what we're looking for on part A. We know this relationship, so now let's use this guy here and see how we can rewrite this so that we can find M3. How can we do that? Well, if I write my enthalpy, so I'm just rewriting, let me grab this. Okay, so let's rewrite that slowly. Let's do substitute where we have M1 by M3 minus 2.5. So I'm going to have H1 M3 minus 2.5 plus H2 times M2. That's also 2.5, so we can sub in 2.5. E has to be equal to M3 mass flow rate 3. And if that's the case where I have mass flow rate 3, I have H3 multiplied, so I have 2.5 multiplying those two guys there. So I can rewrite this as, okay, so if I want to find M3, I'll just be 2.5 that multiplies the differences, right? So the difference between H3 dividing and 3 dividing, so we have M3 here, so it's going to be M3 minus M1, so that's going to be H3 minus H1. And on the top side there, we're going to have H2 minus H1. Okay, so as long as we can find the entropies for these guys, for 1, 2, 3, we can find mass flow rate 3. If we can find mass flow rate 3, then we can go ahead and find mass flow rate 1. Brilliant. So now let's go to our property tables. Let's start with the first one. It says it's superheated. Okay, we can be sure we can look at the 5 bar for the saturated one. So saturated, 5 bar, and the saturated temperature is 151. Ours is 260, so indeed superheated. So saturated, no, superheated. And now I'm looking at 5 bar, and I want 260. So I want something that's between these two fellas here. So I'm going to be looking at these values here. This is what I'm interested in. I'm going to go ahead and grab these guys because we need to find entropy, but also need to find, enthalpy, but also need to find entropy for later. So I'm going to have to interpolate between those values there. So let's go ahead and do this temperature, enthalpy, and entropy. So when my temperature is 250, my enthalpy is 2962, and my entropy is 7.271. When it's 300, this is 3065, and this is 7.46. Okay, so that means that if I want to find things for 260, and you just need to interpolate here, do a linear interpolation. We did a couple of videos on this already, so if you're not sure, I'm going to leave a link somewhere on the top here. And this gives me 2982.6. And for entropy, you get 7.3088. Cool. So we have our values. This is our H1. This is our S1. Next one is the compressed fluid. Compressed fluid, same thing, 5 bar. So we can check our temperature. Our T2 is certainly going to be smaller than Tsat. Yep. So Tsat is 151. Our temperature is 100. So indeed compressed. If I'm looking at compressed, so long as it's not too much compressed, it's not above 5 megapascals, then I can use the temperature table. Temperature table is this one here. Saturated, I'm looking at the temperature. I'm looking for 100. So 100 Celsius. And because I'm looking for the saturated liquid, then I'm looking for this column here and this column here for entropy. Yeah? So this one and this one. So this is my value here. This is my H2, and this is my entropy 2. Great. And then things leave as a saturated liquid. Yeah, saturated liquid, 5 bar. So that's enough information for us, right? Saturated liquid at 5 bar. Let's highlight 5 bar again. This is my saturated liquid enthalpy, saturated liquid entropy. So this is my enthalpy 3. This is my entropy 3. Brilliant. We have everything we need. 640, 419, and the 2982. So let's give it a go here. mass flow rate 3 will be 2.5 kilograms per second. Note how the unit's going to be this guy here because these guys have the same unit, so they're going to cancel each other out. What do we have? 419.1 minus 2982.6 divided by 640 minus 2982.6. This gave me 2.73574. So let's go ahead and do 2.736. Okay, that's M3, but we're not interested in that. We're interested in M1, and that's what we're looking for. So M1, very straightforward. Just need to subtract 2.5 from whatever we found. We found 2.70, so that's going to be 0.236 kilograms per second. Right, and that's the answer for part A. Cool. Now, part B, we need to find the entropy generated here, right? One thing that we need to remember when we're doing entropy is that entropy, as opposed to energy, is not conserved, right? There's no such thing as conservation of entropy. But we do know that if there's an entropy generating, well, we have a process happening here. We have these guys entering with a certain entropy, this guy entering with a certain entropy, and then this guy leaving with a certain entropy. If we're generating entropy, then that means that if I sum up this guy, these guys together, and whatever is being generated, that's going to be the entropy by the end of it, right? If we're increasing the entropy, and we know the tendency is always to increase entropy, then the entropy is going to be the combination between these two. And if we just accounted for those two and made that equal to this fella here, then that will be conservation of entropy. There's no such thing. So if we have any generation, that's going to be also summed up to these two fellas in the beginning. So that's what we're going to do. Set it up like so. By the way, it's an insulated system, right? So this is 0, this is nil, so that's why it's so straightforward. So all we need to do is the sum of everything, so the entropy on 1, but I have mass flow rate, right? So we're actually going to get a instead of energy per Kelvin, we're going to get watts per Kelvin on this. And then 2, this, plus whatever energy was generated, entropy was generated, if any, but this has to be a rate because these guys are rates as well. Then that's going to be whatever's coming out of it. And we have everything, right? We have the masses, yes, we have the entropies, we grab already, so all we're missing is Sgen. So Sgen as a rate will just be my S3 M3 minus S2 M2 S1 M1. We have all the values, we do. Cool, plug and play. So 1.86 times mass 3, the one that we just, 2.736 minus S2, the table here, 1.307 mass flow rate 1, that's the very small one, so what we found 3, 6, and then S1, oh no, never mind, S1 is the one that's very small, this is a big one, so this is 2.5. 1 is the steam, so that should be the gradient. This is the greatest one. We have 7.83, 88, and that's the small one we just found, 236. Great. In terms of the unit, let's just check that quickly. We're multiplying this as entropy, so this is kilojoules per Kelvin per kilogram. That's what the table is giving us. And we're multiplying that by kilograms per second mass flow rate. So these guys obviously go away. And then we're left with kilojoules per second. That's kilowatts per Kelvin. So our unit is going to be kilowatts per Kelvin. Cool. So S generated in the form of a rate is, I got 0.0965832. Let's go ahead and do 0.0966. And that is kilowatt per Kelvin. Okay, so know that we get a rate because this is a constant process, so it's not like we're getting a little increase in entropy and that's it. As long as this process is going for every second it elapses, we're generating an extra about 0.1, right? 0.1 kilojoules per Kelvin. Okay, so that does it for this question. This is our answer for part B. Nothing fancy about it. It's just a matter of finding property tables. It's actually giving us some nice information at the beginning. It says it's compressed, superheated, and saturated. It didn't remember that we didn't need these two pieces of information. We could find that out for ourselves. But it was given, so I guess more power to you when you're doing the exam. As per usual, if you have any questions, let me know, and just put in the comments below. And make sure you like the video if it helped you out. Subscribe to the channel so you're always up to date with the problem solving and tips we release. Talk soon.